Welcome to the Odor Always Moves video series, translating the complexity of odor movement down to the operational level for canine handlers and trainers. This is the third video in the series, and today we're going to be talking about a search and rescue scenario, specifically open water searches. And we're going to cover the topics of data collection and analysis, the triangulation method, and the center of mass method. As always, these videos are all dedicated to my first bomb dog, Daisy, who actually got her start with the Gallatin County Tactical Dive Team back in the day. Big disclaimer here, I am not a search and rescue canine handler or trainer. I don't do open water searches. And this entire video is based on conversations with canine handlers who do this, or human remains detection dogs, as well as even other sources of odor that may be searched for that are underwater, and also dive team members. And just the problem of where a dog may show an indication may not be where the actual source is. And so I stepped back and I wanted to look at this from the perspective of my day job, which is in the engineering consulting business. And so all of the things that I'm going to talk about are based on that. They're not based on necessarily canine. They're based on the engineering consulting field. And how do we look at things and maybe try to solve problems. And hopefully you guys can take this and learn from it. This is meant to just be educational, but take some of these concepts and apply it to your use, and hopefully improve your success rate. Now, for this, it's all about the data. Okay, you can't analyze or manage what you don't know, and so our focus initially is just going to be collecting the correct data and then using it to solve the problem. And in the canine context, that's finding the source of the odor. And what you need to know is the ability to read the dog's change in behaviors, the ability to log these events when they occur, and the ability to analyze that data afterwards. When I talk about changes of behavior, every canine handler knows this. It's basically where your dog shows that it is indicated or that it has encountered a target odor. And this could be anything from a head snap, body stiffening up, tail wagging faster. You know your dog. And the key to this is you have to have the confidence as a handler to say, my dog just encountered target odor. Even if it's only for a few seconds, you have to be able to note that. Now, logging the changes of these behaviors, okay, that's going to be the real critical thing. That's really where the data is coming into play here. And when I say logging it, we are logging the location at the time that your dog showed a change of behavior, and more importantly, the direction of wind at that moment. And the location has to be in relationship to the search area on a known state plane coordinate system, or lat longe, or some kind of system that you can correlate it back to a map or GPS system or GIS system, something that you can actually look at this in relationship to the actual search area and come up with the coordinates based on that. And then the wind direction is critical. Okay, that I cannot emphasize that enough. Now, there is some ways to collect the data. Okay, the easiest is handheld GPS and a flag and a windsock on the boat with a compass. Okay, and that may require you to actually stop the boat momentarily and get an accurate bearing on the wind. But more than likely, this is also going to just involve having a helper, not the driver of the boat and not the handler, but having someone that their sole job is when the handler says change of behavior, dog came into odor, and their job is to now create that waypoint in a GPS system or whatever method you're doing, and then orient and having the name of that waypoint maybe show the bearing in terms of the compass, the 360 degrees, and then they're logging that. Now, an alternative to that, though, is a person on the shore at a known location or in a command boat. And their sole job, and that command boat's anchored, so it's stationary. Their sole job is they're logging the data that's called in by maybe a two-way radio by each team, and their job is to maintain a constant bearing on the wind. And so every time they get a call in, hey, change of behavior, this is our waypoint that we're marking, and then that command boat says, or command location says, bearing of the wind is this. Okay, so that's a way of looking at it. But the bottom line is you got to get the X and Y location, so latitude, longitude, state plane, northing, easting, whatever, and the bearing of the wind at that moment that dog changed behavior. And remember, the more accurate the data, the more accurate the results are going to be. Now, the more data you get, also the clearer the picture is going to become. So if you only get like 1 or 2 points, it's not necessarily going to be that helpful. It can be, but obviously the more data you get, the better. And keep in mind, this is not a short duration thing. This can be data gathered over a day or two. It's not like you're trying to rescue a person. This is a drowning victim. Time is on your side at this point. Okay. And obviously, if your dog gets into odor, it's really strong. You're able to turn the boat into that airflow, that wind, and follow it to source. Great. That's a no-brainer. You do it. But this is where all those times where the dog basically shows a negative and or shows an indication, sorry, an indication that they're in odor, and then they lose it. It's a negative, or the dog, yeah, maybe multiple teams out, and a lot of them are showing changes to behavior in different points. And those are the kind of things that we want to be logging, where it's not a crystal clear follow to source type thing. Now, for this video, we're going to use a scenario to kind of demonstrate what I'm talking about. And in this particular one, this is based at a large reservoir, Canyon Ferry, which is not far from where I live, but it's on the Missouri River, so it's a massive reservoir. It's about 30 miles long, and the water depth at a particular location that we're going to be using is about 90 feet. That'll come into play in a little bit. And here's your scenario: unattended jet ski was found about a quarter mile offshore from a local campground. The person had been seen motoring out on the jet ski without a life vest on, and now they're missing. Okay, so the wind in this area is typically from the west. Now, based on that, what we're going to do is we're going to start our search pattern on the downwind side of our search area, and we're going to do a perpendicular pattern working into the wind, back and forth, back and forth. And the goal is basically to have that dog cross the odor pathway. Okay, and that's why we do the perpendicular to the wind. And again, I'm guessing search teams are already doing this. I'm pretty sure, I've talked to people and they are. So this is nothing new, okay? But it is going to come into play in terms of when the data is collected, okay? So let's take a look at this from the standpoint of just a model. And so this is, as in prior models, this is not to show the actual extent of the odorous gases. There's just too many variables of what kind of gases are being released from a human body underwater. But for this particular model, even though we started our search area assuming the wind was from the west, at the time you actually start the search, it's now coming out of the northwest. Well, we're going to stick to that pattern, that north-south pattern, working westward, perpendicular to the wind in terms of our boat motion. And so we're just going to run this model. And you can kind of see the odorous gases kind of moving. There's some breakups in it, and that's purposeful. So that's a combination of wave action, the wind speed, and also just the odor source is not a constant odor source. And you see, and now it starts shifting, so it's a little bit more out of the north. But then towards the end of the model, it shifts more out of the west, almost from the west southwest. And this, just so you know, this model actually simulates about 30 minutes. It obviously wouldn't be changing that much in the duration. I compressed the time. So what you just saw simulates about 30 minutes. And I did purposely make those changes of the wind just to illustrate the point of the method of triangulation. So let's take a look at this from our first leg of our search. So we started at that northwest or northeast corner of our grid. We're heading south. That first leg, we're not seeing anything. No hits, no indications, no changes to behavior. But on the second part of that leg, you come across a dog shows a change of behavior, maybe a head snap or something that was like, wait, I'm in it, but then it's gone. And that's what I'm talking about when you mark it. You mark that location right where that happened, and you can see the bearing of the wind direction at that time. Okay. And when we continue on, nothing on that leg, nothing on that leg, nothing on that leg, and you can see the wind is starting to shift. Okay. And then on that next leg down, though, dog comes across that odor plume again. It shows another indication. We mark it, and we mark the bearing of the wind. And you can see it's different than the first point. Next leg, no indication. We're out of odor again. Next leg, nothing, nothing. And boom, on that downwind leg or that lower, that southerly leg, we hit it again. And the dog comes into odor again. And then again on that next leg as we head north. A dog hits it again. Each time you're marking that line, that not that XY location of where the behavior change occurred, but that bearing of the wind direction. And then we continue on, nothing on that leg. And then this is now our fifth point, our fifth change of behavior that has a bearing with the wind direction associated with it. Let's take a look at that zoomed in. And you can see each one of those points where that change of behavior occurred. And you can see the bearing of the wind direction, and they're all converging at a particular location. That's the triangulation method. If you don't have the wind data, those points, those XY locations, mean nothing. It's all about the wind, okay? Because the wind is carrying the odor. But the other thing to keep in mind, this whole video series really is based on fluid mechanics. And remember, fluid can be a liquid or a gas. Well, we're dealing with both in this particular model. And specifically, we're dealing with water that is, basically conveying the microbubbles that's going up and hitting the surface. And when it hits the surface, well, the wind carries it whatever direction and speed that it's carrying it. That's all going back to advection, which we covered in the first video in this series. Now, the thing to kind of remember is microbubbles actually rise much slower than regular full-size bubbles. Those of you that scuba dive or played, with snorkeling or something, you blow some bubbles underwater, they rise pretty quickly. Microbubbles don't. The buoyancy is a little bit different in how they behave, and so it's a much slower ascent rate. That comes into play because if there's a current, there can be horizontal movement of those microbubbles, and so where they surface may be very different from where the source is underwater. And then, of course, once they hit the surface, the airflow carries it downwind, and which is where our modeling is showing. We're not showing the underwater modeling. We're showing it when it's hitting the surface and being carried downwind. And so, understanding that there's two forms of advection occurring, one in the water, one in the air, and we have to take both of those into account. Okay. Now, to do the water one, I developed this spreadsheet back when I was helping the dive team, and it just basically tried to simulate the ascension rate for microbubbles based and then horizontal drift of that, and to kind of give an idea of, hey, this is the potential horizontal shift in where that odor is being detected on the surface versus where the source is on the bottom of the lake. Okay, and so for our model, we have the lake depth at that area was about 90 feet, and because it's a reservoir, the Missouri River is entering on the south end and then exiting at the dam on the north end. There is a current in that lake. I don't know what the specific current is. I just picked the slowest one just because it's a big lake, and my guess is it's pretty slow. So that's a quarter mile per hour. So basically, zero point 0.4 feet per second. Okay, it's not a real fast flow, but that correlates to, given the depth, a drift of 103 feet potentially. That's significant, okay? Because if your dog indicates on the surface and you're not taking into account the drift of the water, you could be sending a diver or sonar down that's 100 feet away from where the source actually is. So just something to kind of keep in mind. So when you start putting this information into a map form, you start seeing where, okay, I know where my lines converge. That's where the odor is hitting the surface of the water. But now if I take into account the current of the lake, my search area now extends upstream of where the lines converged, potentially 100 feet. And that's where you start thinking, okay, that's where I'm going to start doing my subsurface investigation, sonar divers. Now, the other method that we're going to cover just briefly, just because it's really the most inaccurate, but sometimes it's the only thing you got, and that's called the center of mass method. And the amount of data that you collect is critical. So the more data points you have, the more accurate your estimate of the source will be. And you're looking specifically for increased density of point locations. All that means is there's more points in a smaller area. Okay. So let's look at that from our model, in our search pattern. Say we did this search pattern, maybe there wasn't any wind or it was a really low wind condition or maybe like really, really slow winds, but it was kind of varying. So dogs are hitting everywhere. If you're tagging those and you're marking those locations, you can see that on this outlier here, so see if I can show this. You can see these outliers here that are kind of on the periphery. But then as you get in, this is what I'm talking about. The density is increasing. There's more points in a smaller surface area. And that's where we want to focus. That's where we're going to be basically saying, hey, this is our approximate area, and this is where we're going to want to send in the sonar or the dive team. But remember, without those wind vectors, it's just not as accurate. So this is kind of the fallback worst case scenario. But the bottom line is the center mass method can work, but you just got to have more points. If you don't have a lot of points and you don't have a lot of indications, that's a problem. But keep in mind, this data can be collected over several days. So if you correlate all of those data points collected over multiple days, you'll start seeing a pattern develop. And that's where the center of mass point comes into play. Now, how do we analyze this? The data has got to be viewed relative to the area being searched. So it can be hand plotted on a paper USGS map, where you basically, if you know your latitude, longitude, and you know how to, account for magnetic north and all that stuff, good navigators can do this. You can actually scale this. If you have the latitude, longitude of these points, you can mark those on a standard USGS quad, and then draw your lines of bearing for the wind and see that conversion point, and then figure out what that longitude and latitude is, and then go enter that into your GPS system and go out and there's your search pattern. But there's also software out there, and I know a lot of the larger search and rescue units and the counties, they have their own geographic information systems departments, GIS, and they're the ones that can help you the most. Okay, they can basically take all that data and put it into, it doesn't take them long. It's really not difficult to do. I do it in my job. That's why I'm saying this. And if they're willing to help you, you can provide them that data. They can do the analysis and say, hey, this is the point of convergence. Go search here. Okay. Now, it's really only by, you know, placing that data on a map and at that correct location, of each point, and then showing the wind vector, that you can determine that source is likely to be, and then you can extract that location, taking into account the current if there is one present, before you send down the divers or the sonars. And the whole point of all of this really was talking to the divers that I know is diving is dangerous. Every time they go underwater, there's a risk. And particularly in really low visibility conditions, I mean, it can be dangerous. And so the amount of times that we can reduce the time, the frequency that a diver has to go underwater, the better. So that's what this is all about. Getting the data, analyzing it, and having a point, a location that has the highest probability of success for when that diver goes down. So that's what really was driving all of this. Now, in summary, we want to collect the data, but it's got to be the right data. It's got to be the location relative to a known coordinate system and can be put on a map, and the wind direction bearing in relationship to a compass, and at each change of behavior point of the dog, and so that you're able to mark, hey, my dog hit target odor, boom, I'm going to note the location and the wind direction. We're then going to plot that data on a map with the wind direction vectors, and where those lines converge is the most likely spot that the odorous gas is hitting the surface. Okay, and the center of mass is the same thing. Okay, it's just the difference is we're just looking for the concentration of points, and that's where that's likely surfacing. And then if there's water current present, we got to take that into account, and for any drift of the gases as it rises through the water. And then the analysis of that is to place those points, that convergence, and then the potential drift due to the water on that map again, to where you can say, hey guys or gals, this is where you go out and dive. This is where you go out and run your sonar. Okay. So that's what we got for this lesson. And for upcoming lessons, the fourth video, we're going to talk more, kind of a follow-on of the second video. We're going to talk about airflows and eddies, continuing that, but more specifically on building interiors and how the air movement inside a building can be impacted by windy conditions outside. And then just upcoming topics, ventilation systems. We're going to show the effects of wind speed and terrain on how an odor plume can lose concentration over distance. And then urban terrains, cityscape, Venturi effect, we're going to talk about that. Buried height is one I'm working on. Thermal convection of air within a room and how that can affect odor movement, and much more. So that's what's coming down the pipe. Thank you for your time. If you have suggestions for videos or you have questions about what I talked about today, please feel free to email me. I will always answer questions to the best of my abilities. And if you want to follow Dante and his antics as a bomb dog, our Instagram is Rotten Bomb Dog. So thank you for your time. I hope this was beneficial for you. Take care.